Thinking about measures of central tendency is much easier when you just have an actual set of data, a bunch of scores, and you just kind of tally things up. You get them in order and you think, oh, well, okay, here's how I can do a calculation to find the average, or here's me putting them in order and having a look at which score happens to be in the middle. So all of our measures of central tendency, mode, median, and mean, are pretty easy sitting in our head when we think about concrete data sets like that. But when it comes to probability density functions and probability distributions, we have to think about these same ideas, mean, mode, and median, through a sort of different lens. So the first one we had a look at was the mode. If you've got something which is the most common score in your data set, then it makes sense that it's the most probable score to occur if you were to choose one at random. So if it's the most probable one, then on your probability density function, you're going to be looking for the highest probability. And that happens in a variety of ways. For example, if you're going to use calculus, then a stationary point, which ends up being a maximum turning point, may be where your highest probability is. But that's not always the case. You've got a function like this where you've got a stationary point down here, but it's a minimum. So you're going to get the highest probability, the mode, existing at an endpoint. And even if you do find a stationary point that's a maximum, if it's a local maximum and it's only relative to that little area, then the global maximum, which is the true highest probability, it's going to be somewhere else. It's going to be on an endpoint also. So this is what we had to look at with the mode. And then we introduced this idea of the median being in the middle of the data set. Now, because I don't know what my actual data points are, I can't just line them up in ascending or descending order and then just say, the middle one is right here, okay? I have to think about what the probability density function will tell me about where the median is. And because the median splits your data set into two, what we can say is that not only is it in two, but it's in two equal halves. If you have a look at the lower half over here, the probability of selecting that lower half, again, if we chose at random, would be 50%. So because that corresponds to this integral down here, I can say that if I evaluate this integral, then it'll give me an answer that's known, a half. So if I'm trying to find the median, so long as I know, like say the lower boundary and what the probability density function actually is, then this median Q2 will be the only unknown left, and so I can solve for Q2 in that way. Correspondingly, or conversely I should say, you could do it from the other end. So if you knew what the upper boundary was, and in some cases with a data set, you only get given a one-sided restriction. So I know we had a look recently at a function, a probability density function, and it was defined in this domain, x is greater than or equal to 50. So in this case, you would use the lower boundary here, but I could do it the other way around. If I said you've got a particular function and it's only defined for values less than 50 or equal to 50 as well, you have to use the upper boundary. And thankfully it's exactly the same technique because the median is in the middle. So from the median to the upper boundary, you should still get an area of a half. So 50-50, total area is 1, like every probability density function. So we've already looked at an example of where you get given the two boundaries and then you have to find the median from that, but you can actually go in reverse. There's no reason why, if you know the median, you can actually go in the opposite direction and find out what the boundaries are, if that happens to be useful to you. So here's an example of how we can sort of play this out. If you get given a probability density function and it's defined as x over 4 within some domain, so you can see here, and I'll just highlight it for you, you've got an unknown on both ends of your probability density function. So you're like, I don't know where I start, I don't know where I end, but I do know, number one, let's highlight it with a different color, what the function is. And I also know, getting onto the questions, I also know the median value. It happens to be 3, right? So how do I use this piece of information to then calculate what the lower and upper bounds are of this distribution? Well, what I'm going to do, just coming back to this diagram here, is I'm going to use these two pieces of knowledge, that from the lower boundary to the median, that will give me a half, and from the median to the upper boundary, that integral will also give me a half. I can use them to evaluate what A and B are, because in this case I know what Q2 is. It's 3. So let's form some integrals. This is question 1. Let's form some integrals that make this statement, right? So the integral from the lowest boundary, which I don't know, up to the median, which is 3, of my particular function, which in this case is x over 4, if I integrate that, that should give me 50% of the score. So its probability will be a half. And in exactly the same way, I can say from the median up to the upper boundary, the upper bound, if I take that same function and find the area that's relevant there, I should get a half as well. So using each of these two integrals and the fact that the only unknown in each one is the lower boundary here and the upper boundary here, I can solve for this. Let's see how that plays out. This particular function, x on 4, when I integrate it, its primitive is x squared on 8. So I'll pop that in here. And then I need to evaluate it at its two boundaries. I know what the answer to that definite integral will be. It's a half. So now what I need to do is do the substitution. Both 3 and a will go into x squared. And so that will leave me with the unknown being a. So let's have a go and see what happens there, right? We evaluate the upper boundary and then we subtract from evaluating the lower boundary. So I'm getting this. That gives me a half over there. I instinctively dislike the fact that there are so many fractions around, so I'm just trying to reduce my cognitive load a little bit. So I'm going to multiply everything through by the lowest common multiple of all these denominators. That'll get rid of all the fractions for me. So in this case, lowest common multiple of 8 and 2 is 8. So I'll multiply through by that. That leaves me with 3 squared, or 9 over there. Leaves me with an a squared here. And 8 lots of a half is 4. So I now want to isolate my unknown a, so I'm going to make that the subject. So I will subtract 9 from both sides. I've got an undesired, subtract 9. I said 9, but what I meant was 4 take away 9, which is -5. Double check that. And then I get rid of that negative. Don't do two things at the same time. All right, now at this point, I want to find what a is. So I take the square roots of both sides, but I notice that every quadratic, when you take the square root of both sides, you're going to get a positive and a negative result here. Now, we've seen in the past, we've looked at situations where instinctively we get rid of the negative result because if it's something we're measuring, like a length or sometimes a time, negative time or negative length don't tend to have a meaning in the situation that we're looking at. But we've also seen that in situations like this, you actually sometimes do want the negative answer, and it's the positive answer you need to disregard. So we don't want to just draw any quick conclusions. We want to think carefully about the probability density function that relates to this question, and then work out what the probability density function tells us about which answer is invalid. So let's go all the way back to the start of the question. And this is something we kind of skirted over because it wasn't immediately relevant to us. If you have a look at this function here, x over 4, we know that because it's told to us this is a probability density function, it has to obey two particular conditions. So one of the conditions is the one that we're using at the moment, which is that the integral from the lower boundary to the upper boundary of this probability density function within the boundaries that are appropriate, it should equal 1. And we're using that fact by dividing that into halves and saying here's the bottom half and here's the top half. So we've already used that fact, but the other condition is that the function within the domain that's provided, it has to be greater than or equal to 0. And the reason for that is because there is no such thing as a negative probability. If something's not going to happen, it doesn't have negative probability, it has 0 probability. So this fact here is relevant to me because it implies a restriction on a and b. Because this function over here, x on 4, it's not always positive, right? If I just draw like a really quick and dirty sketch here, x on 4, what kind of a graph is this going to give us? Well, it is a straight line, x over 4. The x is just to the power of 1, so that's why it's a straight line. And then it's excuse me, sneeze that didn't turn up. Its gradient's going to be very shallow. Do you see that? It's like a quarter x. So it's a very sort of shallow line that passes through the, let's try that again, that passes through the origin like so. Now you can clearly see, even from this very, very rough drawing, that part of this graph is outside of what a probability density function can be. The only part that's allowed is this part over here that is greater than or equal to 0. So what that means is I really need to disregard this left-hand section over here. I know it can't possibly be part of the probability density function. So what I can say is that due to this fact, let's highlight in a different color, due to this fact that the probability density function has to be greater than or equal to 0, and the shape of it has some implications for A and B. Namely, you can see it over here. A and B are x values, right? They're horizontal values here. So A and B both have to be in this positive side. And you can see how this is going to help us determine which of the answers we just got for A is valid and which one is invalid. The way we would state this, the way we would capture it, is by saying since our function has to be greater than or equal to 0 for this particular domain, what this implies is that, number one, A can't be negative, right? So A is the lower boundary, so the lowest it can be is a 0, okay? So it can't be negative, so I've got 0 being less than or equal to A. And I also know that A and B can't be equal to each other, because then you wouldn't have the probability density function its area couldn't possibly add up to 1. So therefore, A can't equal B, so that's why I don't have the equality on that. It has to be bigger, right? But what's important is that means they're both positive. So now when I come over to here, I've got this A equals plus or minus root 5, but I can say since A has to be greater than or equal to 0, A can't possibly be the negative results. So A equals the square root of 5 only. Fantastic. So this is my lower boundary. What I'm going to try and do is go through this same process, but work it out for the upper boundary over here. And thankfully for us, a lot of the working is very, very similar. For example, I don't have to integrate a whole new function. It's still x on 4, so I know that its primitive will still be x squared on 8. My boundaries are slightly different. It's not from A to 3, it's from 3 to B, but they both equal to a half, just like I had in the other situation. You're going to get a very similar thing when you go ahead and evaluate your boundaries as well, because you've got b squared on 8, take away 3 squared on 8. Does that seem familiar? It should. And just like before, my instinct is to get rid of those fractions, so I'm going to multiply by 8, just like I did earlier. So I get b squared minus 9 equals 4. Now things diverge. I'm not subtracting 9 from both sides, I'm adding 9 to both sides. So I get b squared equals 13. And let's continue our working over here so we don't run into the other working. I'm going to get b equals plus or minus the square root of 13. And in exactly the same way as I did before, I can say since b is greater than 0, remember it can't even equal 0 because then a would also equal 0, you're going to get the positive one only, square root of 13. There we go. So just double check, have I answered the question? If the median is 3, what are the lower and upper bounds of this distribution? And the answer is, yeah, I found them. They are right here. A should be root 5, that's the lower boundary, and B should be root 13, the upper boundary. Now, before we progress on to the second question that you can see here, let's just visually confirm what's going on here, right? Now, here's something I prepared earlier. It's the probability density function, x on 4, and you can see I hadn't restricted it when I first drew this because I didn't know where the restrictions were. But what you can see is, for starters, if I zoom in over here, these are the values that we have found, right? First, there was the median, and that was just provided to us. And then we had the square root of 5 and the square root of 13. So where are they? They are on either side. If you go into your calculator and get a decimal approximation for root 5 and root 13, these are the values that you'll turn up with. And thankfully, because I use technology to help me, you can even see the green and the orange areas are looking equivalent because they are indeed equal to each other. So if I get rid of this guy here, those two areas are both equal to a half. And you can see me double checking that using technology to verify the integral there. There's the half and there's the half as well. Okay, so things are looking good. We found our upper and lower boundaries using these implications about the probability density function. What's this next question say? It says, hence, determine the score of the 85th percentile. Okay, so we need to think about this for a second because we've talked about medians for a little bit, and we've heard of percentiles before, but we haven't really talked about them recently, right? So let's think about what is a quartile, or what is a median, for example, right? It is that particular score right here that divides up your data set into two equal chunks, right? Now, we weirdly describe it as Q2 because the median is also a quartile, right? Quartiles don't divide your scores into two groups. as the name suggests, quartiles, they divide your scores into quarters, right? Into 4 equal groups. So I mean, I'm just going to roughly eyeball this, but I would say that the first quartile might be somewhere around here. Okay, Q1 might be here. So, you know, I'd be expecting that this part in here, this area would be a quarter. This area here would also be a quarter. So that would make Q1, that spot in the middle, which divides it up. And then Q3, we've already got Q2. Q3, I'm guessing, will be somewhere around here. Again, this is just approximate, right? So you can see I've now got, and I might as well write it in, 4 areas that are all going to be a quarter. You see that? So this is the way quartiles work. Now, we can just extend this idea, right? Quartiles divide you into 4 groups. Deciles, as the name suggests, dec, they divide your data set into 10 equal groups. And percentiles divide your data into 100 equal groups. So in fact, our quartiles here can be expressed as percentiles, right? You know, Q1, it divides up the first quarter of the scores from the other 3 quarters of the scores, right? So it would be the 25th percentile because you've got 25% of scores before that, and then 75% or above. This guy here, the median, we would also call that P50 because the median is above 50% of the scores, and then here we would say Q3 is the 75th percentile, right? Now, we have a common example, real-world example of this. The ATAR works very much like this, right? So it is like a percentile in that if you've got an ATAR of 99, that positions you in relation to the other 99% of people who did the HSC or did the exam when you did, right? So therefore, if this is the way this works, you can see the implications that this has for the integrals, right? If we want to find where the 85th percentile is, the 85th percentile, like, I don't know, in this one, if this guy here is the 75th percentile, the 85th percentile, I'm actually going to go and put it onto this graph here because this is the actual probability density function I'm dealing with. The 85th percentile should be that point such that 85% of the scores are below it, right? So I mean, I'm guessing it'll be somewhere around here, right? P85 should be somewhere around there because this section here looks like it's roughly 85% of the scores. So the probability of selecting one of those scores at random would be 85%. So now that I know what a percentile is and its implication for area, I can now set out an integral that'll help me solve this, right? Do I have enough space here? Yeah, I reckon. Let's put it right under here. Okay, so question 2. How am I going to word this? Well, P85 is the score such that, I should write this down, is the score that is above 85% of the scores or equal to. So what I can do is I can say, therefore, from the lower boundary, which I know to be root 5, all the way up until P85. This is that black shaded area that I was trying to get at here. Let's make it a bit cross-hatched, a bit more obvious, right? That should be the 85% of scores. So you can see I'm forming an integral from root 5, which is my lower boundary, all the way up to P85, whatever that happens to be. So let's go ahead and form the rest of this integral here, right? So it's x on 4 dx, and that should be equal to 85 over 100. That's the 85%, okay? And what I'm going to do here is I'm going to evaluate this just like I found the lower and upper boundaries, right? This right-hand side, it still integrates to x squared on 8, but I've got new boundaries here, root 5 and P85. The right-hand side there, 85 on 100, common factor of 5, so you're going to get 17 on 20 if you were to cancel that common factor. Now, what am I going to get here? It'll look a bit messy for a little bit, but I can still work with it. I'm going to substitute in my upper and lower boundaries. So here comes the 85th percentile squared divided by 8. And then I'm going to subtract the lower boundary squared. So that's root 5 squared, which is 5, divided by 8 equals 17 on 20. And so now what I want to do is just make P85, the 85th percentile, make that the subject, and then off I go, okay? You're probably getting a bit of the rhythm here. I want to get rid of fractions, so I want the lowest common multiple of 8 and 20, which is 40. Okay, so I'm going to multiply everything by 40, which gives me 5 lots here. Take away 5 lots of 5, which is 25. And then on the right-hand side, if I multiply both sides by 40, 40 and 20 will cancel out, giving me 2 lots of 17 on the top, like so. I've got 5 lots of P85 on the left-hand side, which I want to isolate. I add 25 to both sides. That gives me 59. And then I'll divide both sides by 5, which gives me whatever this number happens to be. This is hopefully starting to look familiar because this is what we had to do with the lower and the upper bounds. I will take the square root, noticing that I have both of them, but I will notice that my x values have to be greater than or equal to 0, and the 85th percentile is one of the x values. So I could have even said, if I wanted to state my point even more strongly, that x has got to be greater than or equal to root 5, but it's sufficient. Like, all I'm trying to do is get rid of a negative answer, so this is sufficient to be able to say that. So therefore, P85 is equal to the square root of 59 on 5, whatever that value is. Now, thankfully, I've already gone and fiddled with this. So this graph that you saw before, I still have it in Desmos here, and you can see what I've done is I've gone ahead and worked out what that square root of 59 on 5 is. It's about 3.435. And so if you put that line in there, that guy there, that is the 85th percentile, and hopefully when you have a look at that, it's not bad in terms of what I eyeballed before. The 85th percentile is pretty high up. I could have worked out what the 85th percentile was by also looking at the upper bound. I could have said that there's 15% of the scores above this, just as much as I could have said there are 85% of scores below it. But hopefully that makes sense, and you can see how I can use this information about the probability density function to find out any percentile or quartile or median that I like.